Gessilan Uchoa, yeah, to here. Gessilan is our PhD student since the beginning of this year, and he finished his master's at the beginning of 2024, and is a young scientist in groundwater river aquifer interaction. And when last week we had the national conference in groundwater from our National Groundwater Association, ABAS, and we would like to deliver you to Gessilan today the Aldo Rebouças Prize that he received from the association. So Gessilan, congratulations for your achievement, and we would like to recognize it in here today. So I showed her. So congratulations, and we would like to thank you your hard work in our group. And yes, and that's it. Thank you. But it's a moment to register this group achievement, and it's not also a group achievement, but also a community achievement. Gessilan is involved with many people here from different groups, and it's very nice to recognize this morning with the presence of Dr. Scanlon. Okay. Also, I have some other information about our group in here. Maybe it's an opportunity to advance in some discussions about groundwater. So our local team is composed by 2 faculty members, so me and Professor Edson, and 2 technicians that are also involved in our laboratory. And we have actually 3 postdocs working with us, 3 PhD students, 8 master students, and 5 undergrads, and more than 40 collaborators in the computational hydraulics laboratory group. So it's our formal name, but we do something more about than computational hydraulics nowadays. Field hydrology and groundwater studies and so on. Our network is distributed in, of course, we have international partners, but we have many colleagues in the whole country, so in the 5 regions of Brazil almost. But we are mainly located in São Paulo, and our studies are in the outcrop zone of Guarani Aquifer system. So that's our main focus, where we have 3 study sites. So we mainly are studying river aquifer interaction, water balance and water cycle in different land uses, and also studying the effect of climate change. And also we try to understand the singularities from urban areas and human used areas, for example, landfills and other structures that can influence in the groundwater availability. Okay, I think for this beginning, it's all the information that I have from us. But from our guest, I'd like to present Dr. Scanlon. And Bridget Scanlon is a research professor at the Bureau of Economic Geology, Jackson School of Geosciences, at the University of Texas at Austin. It's her 2nd time here in São Carlos, right? So we are very pleased to have you again here. And her current research focuses on various aspects of the water resources, including global assessments using satellites and modeling, management related to climate extremes, and water energy interdependence. She has authored or co-authored more than 1,800 publications in the field and also in correlated fields. And Dr. Scanlon is in an AAAS, AGU, and GSA fellow and a member of the National Academy of Engineering in the US, right? So thank you again, and please, everyone, welcome Dr. Bridget Scanlon to our stage. Thank you. Yes, and this is our pointer. Maybe we have to change the presentation here. Just a moment. It's in this one.
Yeah. It's fine. Thank you so much for coming here. Oh, thank you so much for coming here this morning. I really appreciate it, and I'm very grateful for Edson recommending me for the Congress, and am learning so much and greatly appreciate the hospitality of the people here in São Paulo and Brazil, and learning a lot. So it has been very interesting for me. This is the presentation I gave at the Congress last week, so Edson suggested I do repeat. So I'm going to give the same presentation as I gave last week. Work on sustainability of global water resources, considering climate extremes, floods and droughts. I set up the Center for Sustainable Water Resources in the mid-2000s when I was trying to get funding from the World Bank, and I felt like I needed an internet presence, and I thought sustainability was a good topic. I never got funding from the World Bank, but I tried. A lot of discussion these days about groundwater, and I was asked to do a review a couple of years ago about groundwater, and I indicated that groundwater is so connected to surface water that you cannot just talk about groundwater by itself, and so I think that's very important. And what I have seen in the field yesterday and the day before, you know, looking at these connections between groundwater and surface water. I've worked with many people over the years. I've been around for quite a while, and I'm extremely grateful to all of these collaborators, postdocs. David Mello, who was a student of Edson's, visited with us for a year, and many others from different regions, Israel, France, China, Egypt, and then also being at the University of Texas, we have the Center for Space Research. So that helps a lot with remote sensing and GRACE satellite data. They were involved in developing that approach many years ago. And then also various hydrologists in the US and other regions. And then when we did a comparison of global models several years ago, many of the people that developed those models collaborated with us. We never seemed to have funding for the things we wanted to do, so we just did them anyway. So this is the outline for my talk. I will present some background information, then talk about what we learned from GRACE satellites about water resources, and then look at the causes of water storage changes in different regions globally, primarily climate effects and human impacts, because we need to know the causes of these storage changes if we want to develop appropriate solutions to them. If it's climate, then maybe we need to adapt to the climate. If it's humans, if it's pumpage, groundwater pumpage, then maybe we need to reduce pumpage. So it's very important to understand what is happening. And then talk about the impacts on water policy, because governance and water policy issues are extremely important. Some people say we are running out of water, and this is the mantra, you know, we're water scarcity, and I'm not sure that that is the correct mantra, really, because I think I like the World Bank had a blog post many years ago saying too much, too little, and too polluted. And I kind of like that better, because it's important to understand, you know, we need to manage those extremes these days. You know, we have flooding, we have droughts. California, for example, would be in a 3 or 4 year drought, and then followed by atmospheric rivers flooding the place. So we need to understand how to manage and store the water from those flood periods to be used during the droughts. So this is the challenge. And if we say water scarcity, The World Bank had a nice report last year, Groundwater, the Hidden Wealth of Nations, indicating we are underutilizing groundwater in sub-Saharan Africa. And so NGOs and other groups hear this thing, scarcity, unsustainable development, and then they fund things then according to that. So I think we need to have a broader perspective. So here, this is Divi Mello worked on the drought with Edson in 2014, 13, 14, 15. And you can see the reservoirs here in Sao Paulo depending heavily on surface reservoirs, just like South Africa did also. And then Divi used GRACE data then to track water storage changes over this time. Very nice study. And then the flooding in southern Brazil, and I saw this from the presentation at the Congress, so just tried to pretend like I know a lot of things. So downloaded the image. But so it's these extremes, and we have the same in the US. You know, they have 3 or 4 year drought, and then they have atmospheric river, and then they have flooding. And initially, they are very happy, you know, because the drought is ending. But then it keeps raining, and then they have flooding and erosion and landslides and all these other things. So, and then this is irrigation map, because we often say irrigation is responsible for 70% of water withdrawal, Stefan Siebert's work, and then 90% of water consumption. And it looks like South America and Brazil doesn't look like it's heavily irrigated. But after being in the field with Edson yesterday and others, it seems like the eucalyptus is like an irrigation system, just pumping water, you know, to maintain it. So not so different from pumping wells, you know, pumping a lot of water. But so in many regions then we have these hot spots where we have dense irrigation in the US and in India and North China. So I wanted to make this point before I get into more details. And I mentioned earlier that it's very difficult to talk about groundwater without considering surface water, and different studies indicated that groundwater withdrawal, 85% of it, about 85% is sourced from capturing surface water or reducing evapotranspiration. And only 15% then is taking water out of storage, out of the aquifer. So when you look at a regional model, like there was a new model of the Central Valley in California, the pumpage, how much water they're pumping, is about 5 times more than the depletion that they are seeing in the aquifer because of capturing surface water and inefficient surface water irrigation when they do it. And so Lenny Konikow showed this for the US, looking at groundwater modeling and monitoring data. And then Inge de Graaf showed it with the global PCR global water balance. So she ran the model with and without capture and saw about this big difference then on the source of water. So when you pump groundwater, a lot of it is coming from surface water. So now I would like to give some background on the GRACE satellite data. And GRACE stands for Gravity, Recovery and Climate Experiment. These satellites were launched in 2002. So it is 2 satellites that are approximately 200 kilometers apart, and by measuring the distance between the satellites, they can estimate the changes in gravity. And the main cause for gravity changes is movement of water, wet and dry cycles, ice sheets melting. And these satellites are at an elevation of about 500 kilometers above the land surface. So hydrologists would like to have and the resolution of the data is about 300 kilometers or 100,000 square kilometer basin. hydrologists would really like much higher resolution. So in order to have higher resolution, you would have to lower the elevation of the satellite. So they had Gochi satellites many years ago, but the lifespan of the satellite depends on the elevation. And so the Gochi satellite, which was a much lower elevation and higher resolution, only lasted a few years. And the original GRACE mission lasted 15 years. And that was longer than they anticipated because there was low solar activity at that time. So I don't think we will ever get the high resolution we would like from GRACE. But I think it's like a parent. You know, you always want the kids to be something they are not. We should take advantage of what GRACE gives us, which is total water storage, is storage in the land surface, the unsaturated zone, the groundwater, the reservoirs. So it's the total water storage, terrestrial water storage. A couple of years ago, total water, terrestrial water storage was recognized as an essential climate variable by the Global Climate Observing System. So I think that was really nice because I think terrestrial or total water storage is very important in its own right. And many studies, they look at the GRACE data and they immediately jump to, well, is it the groundwater, is it the surface water, is it the soil moisture, without really talking about what the terrestrial total water storage is telling them. And so I think it's good to recognize the value of that. So let's see if this, okay. I hope you can hear the sound for this. Maybe I can raise the volume for you guys. Or on the computer? Yeah, maybe.
Yeah. Yeah, it is.
Oh, it is max.
Yeah.
Very good.
Here
Oh,
it's a little bit more.
all right.
Yes.
Okay.
Yeah.
Okay.
Gravity. It's everywhere. It's the force that keeps our feet on the ground and the moon orbiting Earth. But where does it come from? Mass. That's simply the amount of stuff that makes up an object. The more mass something has, the more gravity it has. Earth's gravity is constantly changing because something with a lot of mass is moving around all the time. What's moving? Water and ice. If you've ever picked up a bucket of water, you felt just how much mass it has. It creates a lot of gravity. Using satellites, NASA can measure Earth's gravity like a scale in the sky. By comparing one month to the next, we can track where the water and ice is going. Weaker gravity means there's less water in that spot. This can tell us where a glacier is melting or a severe drought is drying up lakes. And stronger gravity? More water, such as in the rainforest in the Amazon. Our scale in the sky even lets us measure water deep underground.
So I like that video because it sort of gives us an idea of what GRACE does. And it is, I think it is different from most other satellites because by monitoring changes in gravity, we get a deep, into the deep subsurface, so we can consider groundwater. Most satellites only look at reflectance from the top 5 centimeters of the land surface. And so GRACE is different. By measuring gravity, we get the whole subsurface. So this was a news program that was aired in 60 Minutes in the US in 2014, and there is Leslie Stahl, who does a 60-minute news program, and Mike Watkins from NASA talking about the GRACE satellite data. And I liked this presentation because it gave equal emphasis to the satellite data and to the groundwater monitoring, that the US Geological Survey is doing, because Claudia Font, who works in the Central Valley, had equal time on the program. And so I think that was nice, because I have heard some people think that we only could start monitoring groundwater when GRACE became available. And that's really sad. And NASA doesn't care, I think, sometimes to correct them. But we're depending on journalists to report stuff. So it's difficult going from satellite data to the ground surface because of the coarse resolution, but it's also difficult going from wells and trying to come up with storage changes. So this is the network that EGRAC has, International Groundwater Resources Assessment Center, and you can see there are large areas where there's very little groundwater level data, and this may be because the country doesn't share, or maybe they don't actually have it. And then, many of you know, when you go from a groundwater level change to a storage, you need to know the storage coefficient. So you need to know if the well is representing unconfined or confined aquifers, with a few orders of magnitude difference between those. And in many systems, there's a lot of layering, and you really don't know what the storage coefficient is. So we have uncertainty going from the ground up and the top down. And the basic thing is we need to look at everything to try to constrain those uncertainties. So this is a NASA video, and talking about different causes of water storage changes, and emphasizing natural variability in response to climate cycles in Africa, in sub-Saharan Africa, where there's very little irrigation. And then another area in Saudi Arabia, when I show this, where they have a lot of irrigation, and it's human water use. So nice. Here you can see in the Kalahari region, you can see the GRACE total water storage increasing and peaking around 2011 and 2012 in response to rainfall, changes in rainfall in this region and wet climate cycle. And then you can see declines in storage after that related to drought conditions. And that's natural variability. And then in Saudi Arabia, they see declines in storage in this region that is related to irrigation. This is 87, this is 90. These are the irrigation circles, 2000, 2012. And so a big expansion of irrigation for food security, and declines in groundwater storage in this region. So sometimes it's easy to determine what's causing the changes. If you don't have droughts and it's humans, then that tells you it's a human impact. Or if you don't have irrigation or much water use, you know it's not human impacts. So Matt Rodell had a nice paper in 2018 in Nature, and you can see he's looking at the trends from 2002 through 2016, and this is the first GRACE mission. And the red areas are where we see declines in storage over that time, and the blue areas are where we see increases in storage. So you can see, and then he looks at various causes of storage changes. Probable climate change in red, possible climate change in purple, yellow, possible or partial direct human impact, and green, natural variability. So it's obvious in Antarctica and Greenland and Alaska regions that there's ice sheets melting, and that's climate related. Then in Central Valley, attributed to human, possible partial direct human water use. Natural variability mostly in this region, in your area. Blue showing increase over this time period, and red decrease. And red in this region, and Patagonian ice shield melting. Blue in much of sub-Saharan Africa, related to a wet climate period at that time and drought in this region. But red in much of the Middle East, related to, it can be related to drought, surface reservoirs, and groundwater. Northern India and North China plain. And the blue in much of Australia, because they were recovering from the millennium drought. So he did a nice job of trying to attribute to the changes, because in the past many of the papers just said human water use. And it wasn't all human water use. You know, there's a lot going on. And so we're not the cause of everything. So then this Ashraf Ratib and our group extended this time period 2002 to 21 and looked at the trends relative to interannual variability to see the reliability of the trends. And so again, you see Southwest US declining trends, much of this region in Brazil, and Middle East and North Africa. And so very similar trends going on. And so looking at the time series then, you can see the Central Valley in California, a lot of interannual variability. So long-term droughts, 2002, 2008, and then 12 to 16, and then a very sharp partial recovery, but it never fully recovers. So people describe it as like a tennis ball going down the stairs. You know, it never fully gets back. And then you can see in the Great Lakes region, St. Lawrence region, there was a wet climate period from 12 to 19, and an increase in storage and flooding. So we're never happy, you know. We either get too much or too little. So South America, this is the Paranaíba, a lot of interannual variability and drought period here, and then partial recovery. And then this is the GRACE data for the Guarani Aquifer region. I'll let you guys explain that to me. And then the Middle East and North Africa, so it's sort of a one-way street. Going down. So Iran has the greatest depletion in storage, and this is in millimeters per year. And then the Euphrates drought in this period 7 to 8, and then it stayed dry for many years, and then atmospheric rivers causing partial recovery at this time. Then north. So all of these graphs are at the same scale. So you can see in the Ganges-Brahmaputra region, this has the largest depletion in storage, and there really wasn't any severe droughts during this time period, so it was related to groundwater depletion from irrigation use, and less so in the Indus and the North China Plain. And so now they have the south to north water transfer, so it's maybe stabilizing some. And then the Australia was in the Millennium Drought when GRACE started, and then flooding in 2010, 9-10, and then a drought again. So droughts and floods in much of Australia also. I showed you this earlier, the Kalahari, increasing storage related to a wet climate cycle followed by drought. And this, in this region of Africa, this is attributed to land use change. So changing native vegetation like tiger bush to cultivated land with fallow periods. So big increases in recharge, and then forming ponds at the surface, the water table rising towards the land surface. And so I guess you see similar things when you change vegetation here to cultivated, but maybe not eucalyptus, but some other types of cultivation. So land use change is very important. We talk a lot about climate change, but land use change is also extremely important. And Esteban Jabagi talks about in Argentina, expansion of agriculture, water tables rising, creating rivers and erosion and flooding. So we need to, it's not all climate change. So as good as GRACE is, it's very nice, but it's only a couple of decades. And so it's fairly recent. So I think this study by McAllister and others at the British Geological Survey was very nice, because they went to the offices in northwest India, Punjab and Pakistan and India and Haryana provinces, and compiled groundwater level data, copied the notebooks and everything from these long-term records, and put together a time series of groundwater level changes. And so here, and looking at the expansion of the canal system, so this is the canal system from 1900 to 2000 almost, and you can see expansion of this canal system. So they were irrigating with surface water for most of that time. And so this is the total water storage change over this time in cubic kilometers. So they built up the storage up to 400 cubic kilometers. This is the median value over this time. And even during a drought period, they built up the storage. And then it stayed stable. And then they started, this is the canal system expansion, and this is the more recent tube wells expansion. So millions of tube wells and groundwater depletion. But they still should have, regionally, should have a net excess of water. But locally, you can have depletion, you know, if you have a very intense groundwater extraction. But so I think it's very important for us to consider the long-term context and not just rely on data that came online yesterday. So there's a lot of interest in the US on the Colorado River Basin, because the original law of the river was formed in 1920 to allocate the water among 7 states and Mexico. And that was a wet period. And so they over-allocated the water, and then we have depletion. But now they will be renegotiating the allocations in 2026. So there's a lot of work, decision-making under deep uncertainty, considering biophysical drivers and social drivers. And so this early paper on Grace by Castle and others attributed most of the stuff to groundwater depletion throughout the basin. And then we kind of, when we saw that, we thought, well, there's not any groundwater, hardly any groundwater use in the upper basin. So we went back and looked at it again and did a more detailed study. And there is groundwater depletion in this region in Arizona. This is mostly Arizona, but not, there's very little groundwater use in this region. And then we extrapolated back from Grace with models and other data. And so you can see that this region is subjected to droughts at decadal timescales, and they've been in a drought since about 2000. They call it a mega drought, and so trying to manage the water in this region is really challenging. But you know, and especially for the cities. But as Brian Richter showed in recent papers, there's a lot of irrigation water use for alfalfa. And so that could provide a buffer. And so the cities are buying some of the land in the rural areas and buying the water rights and then transferring water to the city. So now, even though I've talked a little bit about causes of water change, storage changes, climate and humans, now I'll go into a little bit more detail using examples from the US, where we have made a career out of evaluating water storage changes. So this is the GRACE data for the first mission, 2002 to 17. And these are the major aquifers in the US. And this is the total water storage in cubic kilometers over this 15-year period. So about 30 cubic kilometers depletion in the Central Valley, 18 in the southern Colorado River Basin, large storage changes 40 in the central and southern High Plains. And what was surprising is that a slight increase in storage in the northern High Plains. Normally think of the High Plains, everybody says depletion, mining, groundwater, but actually the northern High Plains has been pretty stable. And even the groundwater level monitoring that the USGS has been doing every year since the mid-80s shows that even though there are ups and downs, the net is fairly constant. And then this is the Mississippi Embayment region, which is a big agricultural region also. And the GRACE data is showing very little change in storage. So the yellow areas are very little change in total water storage. The upper Colorado, the Mississippi Embayment, this region here, northwest, the Columbia Plateau, slight increases. And this is a region line that sort of divides subhumid from semi-arid. And so in this humid region, then you can see slight increases in storage. You don't have the droughts that you have in the semi-arid regions, and you don't have a lot of irrigation. So this is the groundwater storage that we calculate by subtracting reservoir and soil moisture, but so the numbers are very similar to what I showed for total water storage. And then if we compare that to groundwater level monitoring and modeling data, this is work that Lenny Konikow did, and the time period is slightly different. We're looking at a longer time period. But what do you think is the main difference between what we see from GRACE and what we see from the regional models in the monitoring data? Where do you see the biggest differences? Pardon? Oh, yeah, right, the Ogallala, yeah, the northern high plains. And where else? Mississippi? Right. So I think, Lenny in his data, he doesn't show as large a depletion in the upper basin, but showed it with the same color because I'm not sure why. But so I don't want to give him too much grief because he works with the USGS and they've been doing a lot of the monitoring. But I think one of the areas then is a big difference between the Mississippi Embayment and the regional model. And as hydrologists, we would generally believe the regional model, right? I mean, it's detailed, calibrated, all of that good stuff. So we were in a group with NASA and the modelers, the USGS, Geological Survey, all together. And so the big question is, who is right? So they redid the model. That early model did not have a dense stream network. And so it underestimated the capture of surface water. And so they did airborne electromagnetics to map the connectivity between the river and the aquifer, and also put a much denser stream network in their regional model. And then they get a lot of recharge and very little groundwater depletion from the revised model. And this came out recently. But when we tried to publish this, the reviewers said they didn't believe us, even though we had the authors of the model too. It didn't matter. But so sometimes you just can't win. And you just move on. So here I'm looking at long-term trends in water storage from 1900. And so this was the data we showed in Northwest India, the British Geological Survey data showing, 400 cubic kilometers of increase and then depletion in the last few decades. And this is the Columbia Plateau in the Northwest US, where they had been doing a lot of surface water irrigation. And so they were building up the aquifer system and then using more groundwater in recent years, and you can still have localized groundwater depletion, but regionally they built up the storage, about 20 cubic kilometers. That may not be a lot. This is another example from the Northwest where they did a lot of surface water irrigation from the Snake River and built up the storage, and more recently have been using more groundwater. But now they're doing a lot of managed aquifer recharge. So during the winter, when they have flood flows, they put it in spreading basins and recharge the aquifer. But it's a basalt aquifer. And so unlike your basalt here on top of the Guarani, it's very high permeability. So it's very difficult for them to find places in the aquifer that would store the water long enough to get them through the dry season. But I mean, we adapt all the time to whatever. And so it's important to understand the history of what's going on. And so now I want to talk about GRACE and climate, the linkage between GRACE data and climate, and I'll use the Central Valley in California as an example. This is black line is total water storage, and this is a linear trend. I know it's a bit crazy to draw a linear trend, but we do. But you can see the drought periods, there is partial recovery. This was a big drought, and then this is the US drought monitor. I love these data. It's been doing it since about 2000, and it just, if somebody says, are you in a drought? And then you just go here, you look at the time series, how bad is it relative to previously and stuff. But look at the drought ending. I mean, overnight, because of atmospheric rivers. I mean, it just blows your mind. I think it's amazing. I mean, not the groundwater depletion, of course, but the surface water. And this happened again last year. Another few years of drought and then atmospheric rivers. And so we have a high correlation then between the GRACE data, total water storage, and the US drought monitor data. Correlation of 0.9. So that suggests that climate is very important in the Central Valley. If we look at the northern high plains, we have a strong correlation too, 0.7. Declines during drought and then partial recovery during wet periods. And in the central and southern high plains, we don't have such a strong correlation with climate because it recharged thousands of years ago. And the only thing that we see is that during a drought, we increase the pumpage. And so that's what's correlated, not the recharge. And then in Mississippi, it's a humid region, so not much drought. The drought intensity is very low in all of this eastern part of the US. And, you have ups and downs, but not much change in storage related to climate. So the other aspect then is human use. And we focus on irrigation because that's the most important thing. So you can see these blue areas showing irrigation, the Central Valley, the Snake River Plain, where I showed surface water irrigation, the Columbia Plateau, the High Plains, Nebraska, Mississippi, very little irrigation in the east. But they're starting to expand irrigation because they think that it would help during dry summers. And the banks who give loans to people want to have a reliable water supply. And so they're asking the people, requiring the people to get loans to have irrigation. So it's banks, it's insurance, it's all these other things that are controlling some of these things. So if we look then at water use in these regions, so here I am just showing a couple of examples. So this is the source of water for irrigation in the Central Valley, and 2010 was a wet year, and the light blue is surface water irrigation and the dark blue is groundwater. So during a wet year, 70% surface water, most of it is piped from the humid region in the north, and 30% groundwater. And then during dry years, then they switch 70% groundwater, 30% surface water. And so it's not just climate that's impacting the depletion, it's also human impacts by sourcing water from different things. So they pipe water from the humid north, but they pipe less during drought because of endangered species issues, delta smelt. And so they amplify the drought because they provide it during the wet years and then they don't provide it during the drought. But having it during the wet years is still good because you can still, that surface water irrigation recharges the groundwater. And then in the Mississippi, we never hear about irrigation and groundwater use in the Mississippi embayment region, but they actually pump more groundwater than the Central Valley. But because it's a humid region and there's a lot of surface water, they can capture a lot of surface water, and so there's negligible groundwater depletion. And so World Wildlife Foundation did a study saying, should we move agriculture from Central Valley to Mississippi? What do you guys think? You work for EMBRAPA now.
I think that we might just transfer the problem to one region to another.
Right. Well,
It's complicated. It's not a simple question.
Right, right. You know, some people say, well, if you were king or queen for the day, what would you do? It's never simple. I mean, they have, you know, sun, they have energy, they have good soils, they can control when they give the water, they have low pests because it's dry, and then they control when they apply the water. Here, you know, you would have more pests. They have a transitory, a migratory farm labor, so a lot of socioeconomic factors and other factors. You know, it's very complicated. And then what people are accustomed to doing, their behavior takes a long time. How much time does it take to stop smoking? Decades. You know, it takes a long time to change behavior and to do new things. So we've talked about the causes of storage changes, climate and humans, and sometimes combined. You know, humans can amplify the climate impacts in different regions. And now trying to look at solutions. I like people in engineering because they're not just always talking about the problems, which I think scientists tend to talk about a lot, but they try to come up with some solutions, and that is really nice. It's a bit more optimistic, you know. I know we have a lot of problems, but it's nice to think that maybe we can try to solve some of them. So I'd just like to present a simple framework, you know, how much demand we have for water relative to the supply and how we change the storage. And so to resolve the spatial and temporal disconnects between supply and demand, then we can reduce demand, irrigation, more efficient irrigation, drip systems. Some people was in some conference and they said, well, if we had drip systems everywhere, would that solve the problem? No, because when we irrigate with surface water, we want to flood it and it recharge the aquifer. And now, because they use the new term flood managed aquifer recharge or ag managed aquifer recharge, then it's legitimate. You know, we have put a label on it, it's okay. But before it was considered terrible to flood a field, you know. But now that we recognize that flooding can sometimes recharge depleted aquifers, so we don't need drip systems. If you're irrigating with groundwater, always maybe a drip system would be important. So it always depends on the context. Food waste, reducing food waste, changing diet. I have not ever been successful in that, so I've given up, and I'm not even sure what diet is appropriate. Because I look at the water footprint that Mesfin McConan has, and so they have the same water footprint for almonds as they have for beef. And so the impact, you also have to consider the source. So the water footprint concept only considered how much water was used. It did not consider where that water was used. And so almonds in California are you know, not a good thing because they harden the water demand. They can't fallow during a drought, and so it's not a good thing. But maybe beef from Nebraska, where they may have enough water, may not be a bad thing. Oh, sorry. So increasing supplies, we generally think of desalination, wastewater reuse, storing more water traditionally in surface reservoirs and now considering more aquifers, managed aquifer recharge. And in the US, we have 1,000 cubic kilometers of storage space that we have created by depleting aquifers. And that's relative to about 800 cubic kilometers of surface reservoir capacity. So, of course, there's energy implications. And we don't have surface water everywhere. We have depleted aquifers. And then transporting water, south to north water transfer in China, the California aqueducts that they built in the middle of the last century. And then food trade. You're exporting a lot of your water in the food that you export. And so important to recognize that. So, you know, reducing demand, increasing supply, storing water, and then transporting water. So in this review that we did a couple of years ago, we looked at the global picture for different things. And so here we have the surface reservoir storage globally, 7,000 to 8,000 cubic kilometers per year. And then managed aquifer recharge is a small amount, 10 cubic kilometers, but locally can be very important. And I think we're seeing a lot of cities in the US anyway, where they're developing a portfolio of options to make sure that they're resilient. They will have managed aquifer recharge, they will have desalination, they'll have wastewater reuse, a small scale, but backup in case they are running out of traditional sources. New supplies, desalination, globally about 35 cubic kilometers. Most of it is in the Middle East and Israel and those places. So, but then the energy implications and the greenhouse gases. But if you don't have any option, you're near the coast, maybe it's a good thing. Then wastewater, about 360 cubic kilometers collected. About half of that is treated globally, and then 11% is reused. So it ends up being similar number to the desalination number, about 35 cubic kilometers. And then virtual water trade, 190 cubic kilometers. So that helps a lot. We export a lot of food from humid regions to semi-arid regions. And then the mega projects, water transfers like the south to north water transfer, about 200 cubic kilometers. So physical water transfers are similar to virtual water trade. So these are some of the ways that we try to resolve spatial and temporal disconnects between supply and demand. And we said earlier, how much irrigation is using globally. And we never think if we're looking for a job, well, maybe I shouldn't be living there, it's a dry area. But Barbara Kingsolver is an author from from Tucson. She lived in Tucson, Arizona, and she said, we have no business living in Arizona, it's too dry. This is the lower Colorado River Basin. And she moved to the humid east and wrote that. And this is my son who has a smoker and cooks lots of meat. And so obviously I had a big influence on him. So, this is desalination plants globally, and you can see the different sources of water: inland water, sea water. You see the Middle East, around the Mediterranean region, a lot of seawater desalination. And Israel, about 80% of their water comes from desal, but they have guarantee the price of the desalinated water for the companies for 20 years. And so a company can invest then if they know they're going to get a guaranteed price for that length of time. And in the US, when they build desal plants, they have a take or pay contract with the municipality or other group, and they are required to pay for the water whether they use it or not for a certain period of time. So there's a lot. So economics comes into it a lot, and then wastewater reuse. China is doing a lot of that. A lot of times when countries develop, they first industrialize, and the environment gets, groundwater gets contaminated, surface water contaminated, and then once they have the money then from industrialization and they develop, then they repair the system. So people talk about impair and repair, but it would be nice if you could skip the impair part and just jump straight to development. And they say South America, Charles Morris Marty says, South America has a lot of potential because you have a lot of natural capital. You have wetlands, you have forests and things like that too. And if you can maintain those in critical regions, then maybe you can do a better job than most of the rest of us. Yes, of course. Maybe some of these are projected. Maybe these are planned. Some of these may be planned. But there's a database behind this paper. Jones and Michel Van Vliet and those guys, So I think even, and so you may be even more surprised with this one. So this is EGRAC's database, so you can check it out. But I mean, I think it's expanding, and they make a big deal about intentional recharge, but oftentimes there's a lot of incidental recharge that occurs from different practices, and I think we need to take that into account. I think what's interesting also is that even in humid regions, they do a lot of this managed aquifer recharge for seasonal water use. They have a lot of tourism and stuff, and so to have water for that increased population in the summer. And then the U.S. Army Corps of Engineers is looking at, when we have these atmospheric rivers, can we store that water, because oftentimes the surface reservoirs, they'll release the water and then they'll have a long drought, and then they say, oh, why didn't you keep that water? And so now they're looking at forecast-informed reservoir operations, because in California, they can see those atmospheric rivers a week out. And so if they see one's coming, then they can release it if they need to. And so they can avoid the problem. But then in Australia, when they were managing the reservoirs during the floods in 2010, they had to go to court to say that they managed them appropriately. Because after going 10 years without in a drought, of course your psychology would be to keep that water in the reservoir. But then they had fatalities, and they had to go to court to say that they were managing the reservoirs appropriately. So this is an example from the Lower Colorado in Arizona. So they built the Central Arizona project to bring water from the Colorado to Phoenix and Tucson. And then these are spreading basins that they created. So the people were accustomed to using groundwater. And so when they put the Colorado water into the distribution system, it dislodged stuff from the pipes. It was not compatible with the pipe system. So then they continued to pump groundwater, and then they recharged the groundwater with the surface water. And the surface water treatment plant, I think, maybe 10 times more expensive to create than doing managed aquifer recharge. And so this, I think, this is an example of the gray satellite data, and it helped to change the policies for groundwater in California, I think. So here you can see the total water storage. This is an anomaly, so starts off close to balanced. And then a little wet period, and then a slight drought during 8 and 9, and then more normal conditions in 10, 11, and then a big drought from 12 to 16, and then atmospheric river, partial recovery, and then up and down. So this visual data, and another drought, and then more river. So this visual data was very valuable, and they worked with the legislators and stuff to pass the Sustainable Groundwater Management Act. And I think having the satellite data, I think when I was younger, if we got data from models, it was like gospel, Now I think you think the satellites are gospel. So these are the basins that are critically overdrafted, and so it passed in 2014 in the middle of that drought from 12 to 16. So it helps to take advantage of a disaster, and then they have to achieve sustainability by 2040. And so it's a bottom-up approach, and they're looking at all sorts of things, managed aquifer recharge and reducing demand, but you have got a lot of big agriculture companies there, and then I think because each basin is working independently, I think there's a lot of double counting and triple counting, not considering upstream what they're doing. So maybe it's going to be complicated. And then this is the pipe system in California that was built in the middle of the last century to take water from the north to the south. And this was a National Geographic article on California's pipe dream. I don't think we would build this sort of system today because it takes a lot of energy. They have to transport the water over the mountains to the south. And so not only do we have to consider solutions for water, but we also have to consider the energy implications these days, greenhouse gas emissions, also the economics, you know. So a lot of different factors to consider. And so this is Mesfin McConan's and Arjen Hoekstra's virtual water. So you can see through food trade, US to Mexico, and all of the different linkages. And so I think this is very, very nice in showing how much water is being redistributed with the food. And then I mentioned earlier, you know, World Wildlife Foundation looking at could we move production from California. So we could either move the water, move the food, or move the people, or there are a lot of different options to consider. But I thought this was a really nice just a write-up just to consider. And then in the Indo-Gangetic Plain, you know, a lot of news articles saying running out of water in the northwest. But then now understanding the importance of surface water, so the World Bank and the National Programme are trying to bring back some of the irrigation canals for some of the municipalities. Some cities in Punjab moving from groundwater to canals and stuff, and recognizing that conjunctive management of surface water and groundwater is very important. The younger generation, you were born after I finished my PhD, so it's quite a different world these days. You have a lot of data, you have a lot of satellite data, and you have a lot of tools, global models, Earth system models, AI, machine learning, all of these things. And then you shouldn't forget in situ monitoring and detailed field-based studies, which we saw yesterday. But more is expected of you, unfortunately. We never get ahead of the curve. But it's fun, a lot of things to try and do. And I think the message is look at as many different data types as you can to constrain your conceptual model of what's happening in the system and try to constrain the uncertainties. So nobody was reading my papers, and so I said, forget it. It's a career to write a paper, get it through review. So I started doing a podcast, and these are some of the previous, and I hope Edson will agree to do, and some of you will also agree to do some in the future. And I have thoroughly enjoyed doing these. And Esteban Jabagi was one of the first, and he has his own videos and everything. And so it's a really nice way to synthesize a lot of things and get things that you wouldn't maybe put in a paper or in a way that you would not express in a paper. And there's also a website with highlights and links to people's papers and stuff. So it's a way to promote other people's work also. So I'm not trying to be famous myself. I'm just trying to promote other people and get the word out and the message out about these things. You know, we have been through COVID and everybody in their own space, all siloed. And so we used to have a meeting every summer. It was a project. And one day in the middle of the week, we had to do something fun together. And it's hard to be allergic to other people if you're doing something fun together. And you learn about their research and everything. And we really enjoyed this. Because we had the satellite data, the NASA folks, we had the ground-based monitoring people, and you know, most of the time hydrologists were allergic to NASA, you know, so putting them all in the same boat, you know, was kind of nice. So to summarize, groundwater provides a really nice buffer for these climate extremes. Sometimes we consider it like a battery that we can recharge during wet periods and use during droughts. And then we need to understand the drivers of water storage changes if we're going to try to resolve them. Some people oftentimes overemphasize human water use, or maybe don't understand the linkages between climate and humans. And then I think managing groundwater and surface water together is very important. And we need a number of approaches to resolve spatial and temporal disconnects between supply and demand. And the satellite data and the models, have helped with legislators and government agencies to develop policies and for decision support towards more sustainable water management. So thank you very much. I'd be glad to answer any questions.
Thank you. Thank you, Bridget, for your talk. It was very nice to see those inspiring examples and also your work from yourself to present to us. And now we are opening for questions. So we have Roberto and Jessilon. And after I would ask you to use the microphone because you have online audience. And afterwards, we'll have a short break for a coffee and to integrate people. So, thank you.
Thanks, Bridget, for the very interesting talk. Also, Edson, for the organization and for inviting us to be here, and I mean, for the whole group. So, first question, first a comment. There was a slide talking about that some colleagues of yours or friends of yours, they were revising this World Bank policies on groundwater use in India. And the Guarani project, the Guarani aquifer has been studied in a GEF project, Global Environmental Facility project, where the main idea has started within the bank. And so the World Bank has helped the countries to develop the idea of getting a project. And on that time, that was in the late 90s, on that time the Guarani project, the so-called Guarani project, was the first groundwater GF project in the world. So this is just a comment. We can talk about later on about implications. Even Ribeirão da Onça was raised within this idea of this project. So the question is, there was some slides or a comment from your side that you showed us that because of the irrigation schemes, there was a catch-up in terms of storage within some aquifers. And then I was thinking myself, here in our tropical conditions in Brazil, where the evapotranspiration is very high, I wonder if that would be the case, or if we are missing something, or I would like to give you some comments about the evapotranspiration rates.
Right. I've really enjoyed going into the field and having opportunity to learn about what's and when Edson and his students and tell me you have 1,500 millimeters of rainfall, I think, oh my gosh, that's huge. We have maybe 300 in the southern high plains, and even in Seattle and Washington, I think it's like 500 millimeters. But it's the high ET then that takes most of that water back to the atmosphere. So I'm not sure that I got your question correctly. Are you wondering if there would be any recovery, or you? Oh, okay. Well, it all depends, if whatever you're irrigating uses up all the water that you're applying, then you won't see much recharge. But in the northwest US, with that flood irrigation, so they were applying a lot more water than the crops were using, and so that's why they had a lot of recharge and a build-up. In Idaho, in the Snake River Plain, they have this thing called the 1,000 Springs. So the aquifer's building up and more discharge through springs, spring flow and stuff. And the canal system in India and northwest India and Pakistan, a lot of leaking canals, and recharging the groundwater. It just depends on how much the crops use relative to what you apply, and if there's an excess then, and if it's an inefficient irrigation. So some people say use inefficient surface water irrigation and very efficient groundwater irrigation, because inefficient surface water is what they're doing in California now. In the winter, they're using flood managed aquifer recharge. So when the crops are fallow, they're flooding the fields when they have excess surface water to recharge the aquifer, and that's the only purpose. And it doesn't negatively impact the crops. So I hope that answered.
Hi, Professor. It's always a pleasure to hear you, and I have a lot of questions. I'm sorry that I always.
But you've been talking to me for the last couple of days.
yeah, but I have a lot of questions indeed. So my question is, in my master's, I work with capture. River aquifer interactions, and I've listened to your podcast with Lenny Konikov.
Oh yeah. Mm-hmm.
And he said. He said something in the podcast that we often forget about the capture, like Thais in the USGS in the 40s. After we have the works from Winter, the Circular 1, Circular 2, and now the work from Lenny. And why is that? Why we often forget that? Because as you talk about the Mississippi Basin and the models, I think from my side, I see a lot of models and a lot of works. They often forgot about the capture, or say I will not modeling that because that's not important. But you see, in even every work today, that this is really important.
Right. Well, I think we think we're smarter now, but we always have to go back and we make the same mistakes over and over again. But having airborne electromagnetic data, they flew a lot of California with airborne electromagnetic data to see where the subsurface river channels are connecting and where it would be best to put the managed aquifer recharge so they would have a better connection with the aquifer system. So we have more data now, to see into the subsurface. We have GRACE data. We didn't have global models of water storage before. But I think it's the economists use the term hedonic adaptation. You buy a new car, you think you've always had it after a few days. It's better to buy yourself small treats and spread them out. So we have global data on water storage. We repeat mistakes, we don't go back to the old literature and see. And oftentimes people are not in the field as much these days. And they don't see things, they're not measuring things. It's a lot of effort to go into the field, and a lot of programs won't sponsor or fund that type of work. But it is so important to collect data and to understand what is going on. And oftentimes, you start to study and you have a concept of how the system is working, then oftentimes you're turned out to be wrong. And that is the value of doing the study, if you knew it ahead of time. I don't know if you ever get reviews back and they say, well, we knew all of this, everything that you wrote about this, we always knew this. Well, you know it because you read my paper. So now you have to say at the beginning, we didn't know this, we didn't know that, So we're getting maybe 2 steps forward, 1 step back, and keep hopefully improving. Thank you.
Hi, Bridget. Thank you very much for your talk. I would like to ask a question, a talk about the how do we lecture groundwater in our programs, in our schools, because, for example, we still teach that we can pumping a certain volume of groundwater as the groundwater recharge, for example. And this concept, this underestimate concept, is still be passing to our students. Our books still brings this concept. So I think there is a problem in the way that we are teaching our students about groundwater management. And so, for example, we don't tell them that we can management groundwater, for example, using flood events, infiltration basins, artificial recharge, and we don't teach it, and maybe we don't know how well groundwater responds to droughts. So, what's in your opinion about this? Because I'm talking about this because several policymakers in Brazil, several professionals in the agencies, still not have. I think the most of them still not have all these concepts. The capture zone, the aquifers capture zone, I think is not be considered. Still not be considered. We think that we can pump as much as the groundwater recharge. So, what's your opinion about all this?
Yeah, I mean the water budget myth that
yes, from the
Brederhoff. Yeah,
yes.
right.
Yes.
But you know, in the places that they have over exploitation, I mean, in the Texas part of the High Plains, they are pumping 10 times the recharge. So if they ratcheted back to the recharge, it might not be so bad. But they are doing 10 times the recharge. It's difficult, you know, teaching because you have so much to cover and you want them to get the basics. And they have to go deep. They have to understand the models and all of these other things. And so it's difficult to teach all of these concepts along with getting through, you know, isotopes and, you know, all sorts of tools and everything. So it's difficult to cover all of it. But I mean, the thing is, you know, when people introduce me sometimes and say I got my degrees here, there, I said, that is like where you went to kindergarten, you know. I mean, it is about as relevant, but we are learning all the time. And so people are looking, and now we have more resources. We have Wikipedia. I know people are allergic to that, but I mean, it's oftentimes where you start and you get, you know, go. And it behooves us to make the information more readily available and try to communicate it in different ways to people and to work with the legislators and to work with the agencies and to work with industry. You know, we want to be siloed and we are so smart, you know, but I mean, we learn a lot. We want to work with the farmers, you know, we learn a lot from them because they are boots on the ground. And so in the oil industry, they work a lot. You know, academics in the oil system, you know, reservoirs, and they work a lot with the industry and back and forth because the industry has very sophisticated research. And so EMBRAPA and working with farmers, our extension people and everything, it's really important to connect. Because you also want to design stuff with them because you need them to uptake that approach or whatever. Or you want to understand maybe you are wrong, you know. That could possibly. So it means more and more communication and more. But we can't be everything. We can't do everything. But so I see the challenge with teaching, you know, the fundamentals and then getting the concepts. But hopefully they read. You know, and then we can communicate in other ways that they will see it.
We have a last question from Mateo.
Hi, Bridget. Nice to meet you. First, thank you for your time here to visit us. And my question is about, are you considered to study some areas of exploration of oil or gas. So it have a change of the, I don't know, in some areas that do fracking, so have some change of the density. What are the behavior of the sensor of the data about those zones? And which, the other question is, which data did you consider or are you considering to enhance the information about those zones?
So I have worked with the oil and gas industry a lot on looking at the impacts of water use on hydraulic fracturing in the US. They need a lot of water to frack and to create these horizontal wells that are, several kilometers long. And then they fracture those, and then they get the oil from the shale, low permeability shale. And in many cases, the farmers required the oil industry to use fresh water and pay them for the water to frack the wells. Early on, the oil industry was using fresh water only because they thought that's all they could use. But then they figured out they could use the water that they produced with the oil and use that to fracture the rocks. That the chemistry, they could change the additives and use the produced water to fracture the rocks and not use fresh water. But oftentimes farmers want them to drill a well and to use the fresh water, pay them for the fresh water, and leave the well then for the farmer to use. So it's complicated. It's not as much water as irrigation at all, but the big problem that we have in the US these days is how to manage the water that they produce with the oil. Because in the past, with a conventional reservoir, a high permeability reservoir, you put it back in the reservoir, keep the pressure up so you keep producing oil. But in shale, you cannot put that produced water back into the reservoir, and you have to put it above or below the reservoir. And then you're increasing the pressure and creating seismicity. And so there's magnitude 4, 5 events in the Permian Basin in Texas related to induced seismicity from putting that saltwater, produced water into above or below the reservoir. And so now they want to treat that water and use it for agriculture or other things. But that water has, it could have the same salinity as seawater, but up to 4 or 5 times the salinity of seawater. And then a lot of other things that even with thermal distillation, they don't get it out. And so it's now they think, they are trying to see if they can treat it good enough quality and then use it for agriculture or instead of disposing in the subsurface. But that is very expensive. It's a difficult question. So maybe they won't be able to produce the oil because of the economics or because of the seismicity that they will regulate them. They can't produce when they have a lot of seismicity. So right now they're dynamically managing that water, and so if there's seismicity here, they stop it here and they dispose it, and then they put it in a different zone or these sorts of things. So I don't know if that answered your question. Gas plays like the Marcellus shale that produces a lot of natural gas in the east. Gas plays produce very little water. Oil plays produce 4 barrels of water per barrel of oil. Conventional reservoirs, mature conventional reservoirs could produce 15 barrels of water per barrel of oil, but they could put it back into the reservoir. So it's a difficult issue, but I don't work too much on it these days. No, not actually grey so much, but INSAR data. INSAR data could show where the land surface would rise, where they were disposing a lot of water, and collapse near Houston, where they were producing a lot of oil and gas. So INSAR data, interferometrics, synthetic aperture radar, are amazing, in showing uplift and subsidence. And even in California, where they do a lot of ground-based monitoring of subsidence, they found new areas of subsidence they didn't anticipate with INSAR, with expansion of irrigation that they weren't aware of. So it's INSAR data that they're using a lot, and GPS data and things like that. Thank you very much, and I am extremely grateful for the opportunity to visit, and I have had such a wonderful time here, and I'm looking forward to continuing to learn about, and it's amazing at the Congress, hearing about one presentation saying how much food you could produce in the future for, global population and things like that, and how much potential there is in Brazil to help us resolve some of our global issues. So thank you for coming this morning. I really am grateful.
Thank you, Bridget, for answering all these questions, and also for your wonderful talk. And also I'd like to acknowledge the audience for also asking the questions. Before we go into the short break, we have a 10 minutes break to some coffee and fruits and etc. We would like to invite our colleague, Jessilyn, to give Bridget a small gift from our country. We know that actually we are better in the female soccer, so that's I think that we would appreciate.
Thank you very much. That's wonderful.
Thank you. So we have like 10 minutes, and afterwards we come back to hear our other invited speakers, and that's it. Thank you.
Pode ser aqui. So, welcome back. Now we have the presentation from Professor Mário Mediondo. He's professor here at the University of São Paulo. After him, we will have the presentation of Professor Didier Gastmans from the State University in Rio Claro. And then after him, we have the presentation of Roberto Kirtchheim from the SGB. Yeah.
Okay,
So
thank
the
you.
floor is yours.
Okay, thank you. Thank you very much. That is the full presentation mode here. Okay. So thank you, Edson, for the invitation. Thank you, Jamil, and all the organizing committee. It's a pleasure, Professor Dr. Scanlon, for your visit. So I'm trying to repeat in my presentation. I'm going to present in rough English. This is a presentation we gave this year in the EGU in Vienna. Of course, I added some slides, and it's also presenting more in the direction of education and community adaptation. This is a project of 3 National Institute of Science and Technology. One is for climate change, coordinated by the CEMADEN, that is the National Center of Monitoring and Alerts of Natural Disasters. The second is the National Observatory of Water Security and Adaptive Management. And the third is about a new initiative for food security. Of course, this is a big effort of different groups, mostly supported by FAPESP, our São Paulo State agency, and also CNPq and CAPES. And here you have some of the groups and initiatives relating to different slides I'm going to present here. This is our group. This is a early career scientist. For our group also, Professor Jamil is here. And here we have this week 2 PhD defense, one from Fabricio Alonso, born in Costa Rica, presenting on Wednesday, and also for Luis Miguel Castillo, born in Honduras, also related to water resources management and more in the direction of surface waters. The motivation and purpose of my presentation is to present some shortcomings we have in one, application of some ideas. That is the DREAMS project. It's a running project. It's a flash drought, even evolution characteristic and the response mechanisms to climate change, considering the spatial correlations. Of course, because of time, I have no time to present all of these results, but the idea is to respond science for policy and education for action. Once upon a time when I visited Charles Boros-Marty in New York, he told me that he's very happy in global scales, but he's very freeze in terms of local scale, because as you zoom and going from top down to the local scale, really you have problems, especially with sustainable development goals. So I put this slide here, try to make a rough comparison between 4 cities. That is pictures I take. This is Montreal in Canada, Montpellier in France, and below you have here Osasco, is a neighborhood of São Paulo metropolitan region, and also Haridwar. I visited this year in India. Haridwar is a very famous site in India, close to the Ganges River. And of course, the point is what kind of similarity we have at the local scales. And one of them, as previously Dr. Scanlon mentioned, is to start resilient communities under changing scenarios of unprecedented extremes, floods, droughts, together, and also pollution and contamination. You see here, of course, in previous times, you have this one. This is the situation we have, for instance, this is very close to Osasco. This is in the Cantarera system. That is a pristine area, close to Osasco, so maybe 20, 30 kilometers from that point. So that is the challenge we have in order to make the integrated water resource management. That means surface and groundwater together, not only quantity but quality, and of course the action of people and into a participatory approach. So zooming into my own history, that is a picture that is myself in the year 1994, close to the town, the city was Professor Edson was born in the northern part of Rio Grande do Sul state, and the problem was related to oxysols. That is an amazing characteristics of our soils here in the tropical regions. For instance, about the high uncertainty when you try to make the, I say, optimization of some models like green-amped models, or even to try an idea of the longitudinal profile. Here, this is the topography of the headwater, and you have here the groundwater, the first groundwater, perched groundwater here, and also you have the regolith or even the rock maintaining all this equilibrium. Of course, this situation reflects in the way we make the parametrization of our models. And you see here, this is the upscale upstream area, and this is related to the saturated conductivity, also maintaining some control related to some kind of macropores, or even piping system you have in these tropical soils. That is very important because when you approach this system only as unimodal distribution of pores, that is the common idea of infiltration models and also for recharge, we lose some characterization about this bypass we have with macropores, mesopores, and so on, and so on. When you split this approach to the Brazilian area, 8.5 million square kilometers, and also some network of stations. Here I present one of them. This is, what? Sorry. Let's try to mute it. This is for the SEMADEM. SEMADEM is related to disaster risk reduction policies. And you see, of course, more concentrated close to people. This is not a representative stations, not for the biome itself, but to prevent people from disasters, droughts, floods, landslides, flash floods, and so on. And especially when you put here in northeast Brazil, you see here Ceará, Rio Grande do Norte, Piauí, Bahia, states, Alagoas, and so on. You see here some of the ongoing stations, agrometeorological stations, that you have an idea of the surface waters and also the storage, potential storage, and also you can follow the monitoring of this water storage in the soils, and also to have an idea of what kind of thresholds we have in order to prevent some collapse about the crops we have in these regions. You have minifundial owners that depends of the content of water in the soils. The way you introduce the monitoring and in real time, you can prevent the collapse of crops in these regions. That's very sensitive. On the other side, for instance, in southeastern Brazil, that is the Cantareira system in the upper left here. It's very interesting because in the middle of the drought, in between 2013 2015, we introduced some new monitoring. Here it's about 17 headwaters, also making the monitoring, the installation, the setup of the stations. And we compare with different kinds of water yield and scenarios. what was very interesting to know that in the drought scenarios we have, that is monitored also with different headwaters, with more or less forests consuming water during the droughts, we see the evidence of groundwater in the middle of the crisis. And that is one of the pictures we can introduce in order to, say, promote the surface waters. Sorry, there is a map inside. This is the global map. So recently, we compared this situation in southeastern Brazil with more 44 cases around the world, floods and droughts, about impact, hazard, exposure, vulnerability, and management, the different case studies, and the way how can we learn or not learned about previous disasters and recurrent disasters we have in the future. So if you have one drought, in the next 10 years you have another drought, we compare the way the institutions have learned the way to mitigate the new drought in comparison with the other, or even the flood, or even both. So that is also the summary at the same time of the Panta-Ray scientific decade. You know, you have 3 decades, the PAP, prediction in engaged basins. The last one was the change in hydrology and society to introducing the comparison between water demands and water offerts in a changing environment. And now we are starting a new scientific decade that is the helping. Helping means hydrology engaging local people in a global world. Professor, thank you very much, Professor Edson, preventing some risk.
Preventing risk?
Yes, especially for your colleague. Thank you very much. So, and this is very interesting. How can we learn from past unprecedented droughts and floods, or even pollutions, and so on, in a different scale? And also, again, relating to Charles Boros-Marty at the local scales. So the local scale is in the middle of the scientific decade. So, and also the summary is solutions. So in this way, in this proposition, we have the DREAMS project. That is also a summary of some research topics, research methods, and operational questions related to droughts, and in comparison with the Sustainable Development Goals. This is very theoretical. In terms of application, you have in this graphic here the precipitation time series, for instance, an example, and different index, SPI and so on, index you have in continuous way, and also we are dealing with the propagation of droughts in time. And one proposition we have now is what will happen if we can make a decomposition of the transfer or the time propagation of the drought. That is the theoretical one, and some managerial factors. So managerial factors are related to climate change, land use, water habits, and the relation you have at the river basin, again, groundwater and surface water, between water availability and water demand. And if you put in an adding approach, we can introduce it to the policymakers, decision makers, in order to accelerate or to break the propagation in time. That is very important, because for a policymaker, knowing if you are under or not under drought, you have different policies, water pricing or even water savings. Now we have compared with other situations in the world. This is an interview, a survey, enhancing drought resilience answers about the vulnerability assessment for small farms. In this case, this is a global expert survey from multidimensional indicators and having different kind of expertise: agriculture, climate change, anthropology, climate science, drought hazard and disaster risk, economy, environment and science, geography, health, hydrology, interdisciplinary data and information science. And also, what was very interesting, the experience of people making the answer was very interesting because they are experienced people, senior people. And what we have made of evidence that we have multidimensional indicators and that it's very difficult to make the prognosis or the drought propagation in only one shot, only one indicator for one country. Coming back to the physical approach or ecophysiological approach of the evapotranspiration related to this water balance, like in the upper part, that is coming from Igleson, the Pete Igleson approach in the 60s, and introducing it in a regional scale of South America. You have some coherent approach or co-dependent system like Amazon or a tropical basin with a local basin like Southeastern or like here in São Carlos, for instance, or the Cantareira systems. Usually you are small or medium-sized catchments with a big water demand, like in São Paulo, Campinas, even in São Carlos. And also relating not only the natural fluxes, but the green water footprint, the blue water footprint, and also the gray water footprint. And that is very important because the pollution we are creating now in Brazil, for instance, if you put all this pollution in rivers and you need the stream flow of this river to make the auto-depuration of this pollution, mostly speaking, we are using half of our country to make auto-depuration of our rivers. And this is very funny. That is one important point for my message. The second point is about the efficiency we have. As I mentioned before in the corridors, in São Carlos, for instance, this is São Carlos. You have the Meio aquifer, this is very polluted, this one. And you have also the basalt here, the rock here. And you have the aquifer here. But the point is that we have, speaking in average size, in average term, 2/3 of our water we are consuming here are coming from this aquifer. That is one point. The second point, the other is for surface water. So we are in the tropical winter, very drought moment. So all the water facilities are very hurry up because they have no water, no surface water. But they are pumping more water from the groundwater. The second aspect is in some parts is confined. So you have some pumps here into the confined aquifer. And in the other parts is free. And part of these areas, like in the Onça River, you have some evidence of recharge. That is aquifer. There are people here. And the second point is we are introducing more people in this surface that it should be forbidden. The Cidade Iraci, another downtowns here, close, more than 1/3 of the people are living in the wrong place. And this is São Carlos, but it's a very good idea what will happen in other cities in Brazil. The third point, what about the efficiency? So we have extracting 2/3 of groundwater, 1/3 of the surface water. What is the problem? We are losing 50% of this water in the leakage of our systems. That is very funny. That is crime. For every liter, for every glass I drink, Thank you. 1 glass was lost. And 2/3 of this lost water was coming from the groundwater. Yeah. Thank you. So for that reason, we need to introduce some socio-hydrology aspects, not only in terms of very nice words, but in terms of water policy. So we are going to return to this, to the final if we have time. I have time. I have watches, but I have time. Okay. And also we can expand it into South American scale. That is one of the PhD presentation for this week. This is for instance, the Guaíba system. That's the Guaíba system. You have the 5 main tributaries. That is Porto Alegre, when you have the big floods this year and the last year also. And also you can introduce the models into an online approach with a community model that is open source code, and to make to study interactions between the surface and groundwater. Of course, it is related to the IPCC adaptation mechanisms and mitigation mechanisms. This is time here, and this is the mechanisms that is IPCC. And of course, in the middle, in the core, you have education. Education, what kind of education? Primary, the high school, and higher education, mostly. Of course, that is the approach for the mitigation between models, data sets, and actors for different projects. This is very important to know, but at the global scale, we have different initiatives, UNESCO HP, UNEP, World Water Quality Alliance, for instance, WMO Strategic Plan, Early Warnings for All, and the COP 30 would be next year in Brazil. At the national scale, we have some enactments that are very important. In the last 27 years, maybe we have the most iconic, the most challenging acts in Brazil. So if you have water, we have loss, what will happen? We have very bad water quality. So this is the moment of action. And this is some slides. I'm going to finish. Initiatives in the schools. This is a primary school in Analândia. This is Corumbataí, catchment of Piracicaba, Capivari, Jundiaí, big catchment in São Paulo. And also related to the water security index, related to economy, resilience, ecosystem, and human aspects. And of course, you can color Brazil in different ways, coming from different factors, and combining them with climate change, for instance. But what is the fourth problem? We have no connection until now with education. It says that this figure says nothing about education. So this is the moment to introduce education link, or the nexus. Water, energy, food, ecosystem, and education together. That is the more than 800 headwaters in the upper Corumbataí. In Analândia here is close to 1 hour by car from here. This is a UNESCO proposal site. Maybe in the next 5 or 10 years going to be officially a UNESCO site. Of course, there is some aspect relating to games, and that is also our model here, introducing people very close to the situations. Now, the University of São Paulo officially is promoting these extension activities being introduced in a hard mode, or explicit mode, or a hardcore mode into the classrooms. We need some philosophy about that. So here is Professor Nancy Doubleday from McMaster University this year, making a summary with students also visiting us, and also with Professor Jamil here, introducing some aspect of the next, the new monitoring site, approaching these socio-hydrological aspects between groundwater and surface water. Here we see here, this is very interesting because we see the Brazilian students with the Canadian students exchanging ideas or even experience about, of course, tropical and cold regions. But very interesting because you have difference between biomes or climates, but the problems are very, very close to each other. That is very interesting. And also we have the possibility to introduce free of charge these education initiatives. No matters if you have not still a publication, you have the Digital Water Globe. That's a starting initiative for the IHS in the last 2 years, when was the 100th birthday of the association. And it's also a tool for networking knowledge in hydrology, especially the early career scientists. Usually you have not enough papers to have a visiting card for yourself, but you have some ideas to share with the others. So this is our associate editors. One of them is representing Brazil here, and the others are coming from different continents. And also the possibilities we have, so my presentation will be available for you all. And of course I can attend in Portuguese or in Spanish, if you like. And also the situation or relating with the UNESCO HP 9th step we have now with the 5 priority areas: scientific research and innovation. The second is water education in the 4th industrial revolution, including sustainability. Bridging the gap between data and knowledge. Integrated water resource management under conditions of global change. And the water governance based on science for mitigation, adaptation, or resilience. That is until 2029. This is very close to Agenda 2030, and also very close to the new Helping Scientific Decade. As it was last week, that's also, Bridget mentioned it, Arjen Hoekstra. Arjen Hoekstra was a very old friend. We lost him in the year 2011. And we have also part of his group, is my colleague Martin Kroll, that gave also seminars and courses. This is also graduate and undergraduate students also last week. Also here is Jamil here, our deputy dean, and also people from the academy, maybe here also. So that is my presentation. So now, about water, I invite you to visit, maybe in some questions, when we are freezing some questions, to know more, because it's aligned to the north here, to the south here, how we have the water problems in our region, the local scale. So I give one example to Bridget. My question, Bridget, is, did you ever handle one aquifer in your hands before?
No.
That is the first time. That is a virtual water a gift for you. What is your feeling that you are handling an aquifer in your hands?
Very powerful.
And you have the feeling of identity, that maybe you have some connections because you know the scale, the landscape. So this is too heavy for you? Not, no? But it's the same way I have the other. This is the same aquifer. So what's the problem? Usually I have no idea that there is a Dr. Scanlon maybe 5 kilometers away from me. And sometimes I have no idea we are part of the solution. You know, we are part of the same situation. We are part of the same, say, aquifer. And that is maybe the 5th, thank you, challenge that we need to introduce into participatory, say, and feasible hydrology. And hydrology is groundwater, surface water with people. Yeah? So thank you very much.
Thank you so much, Professor Mario, for your very nice, insightful presentation. And it's very interesting that you are working with hydrology from very different perspectives, and this is so nice. Now I would like to invite Professor Didier to present, and I will ask you guys to share, to save the questions to the end, to Mario and Didier. Okay?
So, before we start, I would like to thank for the invitation. Myself, in the name of my research group, I would like to apologize because I just arrived from the field on Saturday. I haven't time to translate my slides, so I picked some slides from a presentation I did 2 weeks ago in Ceará, in Crato, and insert some results from our field work. And something that I would like to say. So I'm working a lot with environmental isotopes, and my main research goal is to introduce stable isotopes and environmental isotopes in water management agenda. And we have a lot of information that we can obtain with applying environmental isotopes. So I will share some results from a monitoring program we are doing in collaboration with COGER. COGER is the water management organism in Ceará state, so they are responsible by the water management, and in my opinion is one of the most important state agencies that make policies for groundwater. They are in so many aspects behind or in front, ahead of São Paulo State, for example. So this project, so a little brief about my talk. I would like to say something about the reason that they contact us to do some monitoring program in Ceará State. Why we should use stable isotopes? How is the development of this project? Some results from 2 sites. One is in the south of Ceará State. It's one important sedimentary basin, Chapada do Araripe, and the other one is in the north between Ceará and Rio Grande do Norte. So something interesting is to see how water is managed in different ways in 2 states that share the same groundwater. It's a case of a transboundary aquifer. Long time ago, Anna did some studies, but both states are not able to talk about how to share this resource, and there are so many problems. And based on our first results, I would like to introduce some ideas about a recent funded project by CNPq that is related to paleotemperature and paleoarchives on groundwater. So basically, COGER is one of the first state agencies that start monitoring groundwater. They start do this more than 15 or 20 years ago. So they have a very interesting network on the main aquifers. So they have a lot of groundwater usage close to the ocean, because there is a touristic activity very high. They have the Chapada do Apodi aquifer, so in the Potiguar Basin, where an economic development based on irrigate agriculture is increasing since the end of the 90s. I worked there drilling wells long time ago, and I had the chance during this trip to visit one of the wells that I worked in, so it's nice for me. And more interesting is that this well was drilled for irrigate melons, and now the water is used to feed water for population. And Chapada do Araripe also is a very important region in the southeast portion. In the semi-arid region, there is a crystalline aquifer, so rocks, bedrock aquifers with low production. Basically is that. So why we should use environmental isotopes in groundwater? This is a nice picture from a paper from Scott Jasescu that he did a very good review on application of isotopes in groundwater. So we can try to understand better recharge mechanisms, mixing of water coming from different flow lines in regional aquifers, upward water, downward water, mixing of waters, interactions between river and aquifers, and I guess in terms of groundwater management, something that few people pay attention about that is the residence time of groundwater. So we have very, very old groundwater, and we mainly don't have any renew in this research. So this is 2 points that environmental isotopes should be incorporated on groundwater or water management plants. So backing on the basic physics about isotopes. So everybody knows that an atom is composed by a nucleus that is composed by protons and neutrons. Protons is a positive charge, and neutrons no electrical charge, surrounded by a cloud of electrons with negative charge. What do the isotopes? Basically is the nucleus, where the mass is concentrated. So an element is constituted by, or we can represent an element based on the atomic weight. So it's the sum of neutrons and protons. The number of neutrons that define the isotopes, because when you have an increase in protons, we change of the element. We move for another element. And the variation on this number, or the number of neutrons in the nucleus of the atoms, produce different isotopes. So isotopes, basically, environmental isotopes, going to elements with atomic weight about 34 is the sulfur, but there are others. And we have stable isotopes in the black line here, which means they remains stable and they don't change their phases. But we have also the unstable or radioactive isotopes that are unstable. So the nucleus has more neutrons than can be catched in the nucleus, and they need to explode, producing some kind of energy, and to become stable. So we can apply even stable isotopes on hydrology or unstable or radioactive isotopes. What means, for example, for oxygen, we have two stable isotopes. We have more than two. So we have 3 stable isotopes, 16, 17, 18, and we have some others that are unstable. What means one oxygen 18? So it means that instead of have 8 protons in the nucleus, they have 9 and 2 protons more, which means about 20% more weight than the regular one, the most common isotopes. This is impacting something very important. We have the light water that encompass almost 100% of the water available in the hydrosphere, and we have heavy water. Heavy water represents a little part, few part of the water amount, but it plays a very important role. Something important, light water tends to evaporate, and heavy water tends to condensate. Basically is an application of gravity law. If everybody understands this process, everybody is able to use stable isotope in any hydrological problem. But someone can ask me, okay, if light water tends to be evaporated and heavy water tends to be condensated, all heavy water is still on the ground and light water on the clouds. But no, because we have this variation in the amount. And what we have, when we have evaporation, most of vapor is composed by oxygen 16. But some molecules of oxygen 18 or deuterium also going up. In precipitation, exactly the same. And this fractionation depends on the energy you have in the environment. So temperature plays an important role. As much hot, in a much hot climate we are, the amount of oxygen 18 that go evaporate will be greater than in a cloud. And this fractionation produce we call the isotopic variability in tempo and spatial scale. So in parts, different parts, we have this variability. This is important for what? If one water is recharged under different climatic conditions that we have today, the water has a different fingerprint, isotopic fingerprint. So basically is when we evaporate water from the ocean, we have a fractionation, an enrichment factor that produces a vapor with one isotopic signature. The first rain produce a first water with almost the same composition of the ocean, but the amount of vapor in the clouds becomes fewer, and the second precipitation has another composition, the third. What is controlling that? Basically is when we have hot climates, lower altitudes and lower latitudes, we have more enriched isotopic composition in precipitation and in groundwater or in surface water. And when we moved for colder conditions or high altitudes and high latitudes, we have more depleted isotopic signal on the water. Something very important too is the determination of residence time. We may have in a region very young water, so that is recharged in a time frame, in frame time of our planet, our water plants, so maybe 15, 20 years. Or you may have some very old and pristine water. So we need to know, about the age of the water to protect the young groundwater from possible contamination source, or to protect older pristine water to overexploitation. This is something that we are looking here in São Carlos, in Araraquara, in São Paulo State, when we talk about the Guarani aquifer. Even in northeast Brazil, we also are looking for the same problem we see here in southern. So this is, I will go straight to the problem. So in Ceará, we are studying this portion, two sedimentary basins, so Potiguar sedimentary basin. Both basins are related to the open of the continents. And the sedimentary basin of Araripe in the southern portion. If nobody have thought about this region, is where people found the fossils, the fishes and the insects. Is a very nice region to visit. It's really, believe on me. Maybe Gisela could talk a little bit more about that. And also is the region from O Padre Cícero. We have two kinds of aquifers here. We have the sandy aquifers and we have karst aquifers, especially here in Potiguar Basin, because some part of the position was released some carbonate platform. So this project has some specific goals. In the north, in the Ceará state, we are monitoring 10 wells, 7 in Açu aquifer, that is the sandy aquifers, 3 in the Jandaíra aquifers, the aquifer, the carbonate aquifer, and here in Chapada do Araripe, 30 wells. Basically, it is a 3 years monitoring program. People from COGER is taking samples every month for stable isotope analysis. We are doing some C14 analysis to determine the residence time of groundwater, and also using tritium, especially here. I will show you something. And so basically is to observe the occurrence of recharge. The question is, even in confined or very deep aquifer, is there any recharge taking part at that time or not? Estimate the residence time, and also collaborate with questions raised in previous monitoring programs. They are doing isotopic monitoring since 2004, I guess. They have data, a very good data set. But basically, in my opinion, understand the water movement in these both aquifers can help them to better, to better manage the water at the region that is basically a semi-arid region, and they count only on groundwater. So on monthly basis, people from COGER go to the field, take the samples, measure some basic chemistry and hydrodynamic parameters, send us samples for stable isotopes analysis that we prepare and send to the Center of Stable Isotopes in Botucatu. They have IRMS to do that. On monthly basis, on semestral basis, we collect sample for tritium, and for carbon-14, we send to CDTN in Belo Horizonte, is the Center of Development of Nuclear Technology. They have a mass spectrometer to calculate the content of tritium, and carbon-14 we send to Beta Analytic in Miami for C14 content. Basically, I will start talking about Chapada do Araripe, the southern region. There is a succession of sandy, shale, carbonate here, where the fish are concentrated, the fossils are concentrated, and in the top we have a cover of sandy aquifers. Basically, until we started the project, the hydrological conceptual model is based on three aquifer system. So inferior, medium, and in the top, bounded by two aquicludes. Brejo Santo is here, is a shale aquifer, and Santana only in the plateau of Chapada do Araripe. And the water is expected to enter in the high and flows towards the lower portion of the basin. So this is the location of the wells. So here is the cliff of the plateau. Here is the valley. We have big cities here, Juazeiro do Norte, Crato, and Barbalha. There, I guess, we have about 500,000 people living in this region. It's a big region. And small cities surrounding around. And at the top of the plateau, there are some plans to plant soybean, using groundwater for irrigation, because there is no water. And people are very concerned about that. Because, for example, Crato and Barbalha are here. They depend too much of the water that flows by these springs here to feed the population. So we have two wells located in the plateau. This is a very deep well with almost 1,000 meters deep. One small wells. We take samples in these springs along the cliff, and more 28 wells in this on the valley. We decided to keep the classification of the aquifers based on the information we had and the classification they used a long time ago, but I think that at the end of this project probably we will change something. Basically, we can observe a large variation on the isotopic composition. We have more depleted, more enriched here, and a little bit more depleted here. That spreads along the meteorological waterline like this one. There's any relationship between the evolution of the isotopic composition and the electrical conductivity of these waters. But when we look a little bit more close, we can define 3 or 4 groups of water based on the isotopic composition. So this is the main rain or precipitation composition. This is the main the variation of this group. Here we have the springs, and here we have something more depleted than we expect for the most part of the water. But this is something interesting. Groundwater doesn't correspond to the isotopic composition of the precipitation. When we start to think about what is the groundwater age of these springs, we talk that this water is very recent. So we decide to use tritium. Tritium has a half-life time about 15 years, and it is able to capture residence time until 50 years. And we were very surprised because all the springs have no content of tritium. So they are older than we expect. This is a problem because everybody thinks that, okay, if we have a very good winter or summer period with a lot of rain, we will see an increase in discharge of these springs. And this is not in fact. And so the springs are very nice. There is a thermal park. Abaiara is a very beautiful place. When we look for the carbon-14 groundwater ages, we observe a relationship between very old groundwater from this well and an increase on the residence time. But something that complicated a little bit our interpretation is the geology. If you remember, this is the conceptual model. This is the reality. So we should think about how this structuration can contribute or to direct the flow or to block the flow. And because of that, we have very young groundwater close to very old groundwater. And we decided to use something like a combination of stable isotopes and residence time. What we observe, so the more enriched isotopic groundwater has a high content in carbon. This one, a few older, and this one is very, very old. And when we look this in the map, we can see that old, young groundwater belonging to this group are close to the plateau. So it depends on the discharge of springs to have young groundwater. And when the flows move to the north, groundwater becomes more and older and older. So this is a little bit what we expect when we look the first piezometric map produced for this region. So the groundwater flow is from high to the low part. It's also a gravity effect. Water moves to high to low parts. Moving to the other basin, we have a few wells here. 3 in the carbonate rocks, 10 in sand aquifers that represent different conditions of circulation. So the carbonate has a lot of evaporation because water was stored in ponds in the terrain and then infiltrate, and you have evaporation. They are more enriched, close to the isotopic composition of the precipitation. And in the Açu, we have a mix. But this is interesting because in green, in strong green, we have the outcrop of the aquifer. And even here, the isotopic composition is almost the same. When we look for C14 data, we have very low content of carbon in all this region, including in one well drilled in outcrop area, and very young groundwater, not so not so young, but young, in outcrop area. What is the problem? When we did a cross section here, so we can observe in outcrop area there is young groundwater. When we move towards the world, groundwater become more and more older. But the problem is that we have signs of over-exploitation of this aquifer that is confined. But these units also store salty water on the back, on the bottom, and also store oil. There is, I guess, one of the most productive regions of in onshore in Brazil, the northeast, the Potiguar Basin. So if we start to pump the water and produce decreasing the level, we may have some salty water intrusion. It should be very interesting if something like that occurs, because it's something, I guess it's the only case in the world that I have heard that we can have salty intrusion in onshore, not in the line of the coast. And we are concerned about that. Because of the older age of the groundwaters that we observe here, and we know that the first study relating groundwater and paleoclimate archives was done using noble gas in the 90s by Mikkel Stoet in the Parnaíba Basin, and he said that the temperature is about 4 to 6 degrees below the average temperature we observe today. We decided also to apply for a CNPq project to better understand the information we have here, to reconstruct the Pleistocene and Holocene temperature using noble gas and groundwater. So basically what we know about old groundwaters in this region and the temperature is something done by the group of Professor Ricardo Hirata in Recife and Pernambuco Basin. This study from the 90s from Michael Stoet, and some information, but only related to 2 ages, done by a student of Gerson from Rio de Janeiro 3 or 5 years ago. And we decided to better understand that. So we have some information here provided by Espelho teams. 3. Go ahead. Yeah. So this is the project. This is the flow line. So the groundwater flows in this direction. As I said, we just returned from the field. We did 2 campaigns, one in January and the other one this month. We sampled about 40 wells for stable isotope and hydrochemistry, 20 well sample for C14, C13, and 12 wells sampled for novel gas. This is one of the proposed. Some pictures of the field. So Natalia, she's here, did a very good job. Very hot. Very nice landscape. So here we can see the plateau of the Jandaíra aquifer, and here the Açu aquifer. So basically the team of my lab that are working on this project, I would like to say for all these people. So we have Natalia, Mariana will do some modeling, and undergrad students. And finally, I would like to invite everyone here to join us in our 15 postgraduate program congress in November. The activities we are working on this. We will invite someone from Washington State University. I guess we can receive papers from you. We have a presentation of paper. Also, I guess it's a very good opportunity to share the groups. So to put the group together like you guys did today. I guess this is important. Everyone is invited, from Murilo, from Edson, from Mario. I guess everyone group is invited to participate on that. They have Instagram page. I guess the Instagram page is Encontro Geociências. If you want to know more about that, please follow us in Instagram. And I hope to meet everyone there. Thank you.
Thank you so much, Professor Didier, for your interesting presentation. Now I would like to invite Dr. Roberto from SGB to present some insights for us. We are a little bit out of time, so I will ask you guys to save the questions to the afternoon, and then we can start the afternoon with a Q&A section, and that's it.
Before Roberto starts, we'll just check the schedule. We have to stop at 12. But Professor Scanlon has an online meeting at 12:30. We'll have a short break for lunch. But we go for a longer lunch. We can take 1.5 hours. We come back at 1:30 after your meeting. So you are going to speak to lunch. Okay, so at 12 o'clock we make a break and then we go for lunch.
All right. So thanks for everybody. I don't have any PowerPoint presentation, so I will be more on talking. Before, just a couple of minutes ago, my boss was sitting there. She's a hydrogeologist, Andrea Franzini, and she needed to leave earlier, so I just wanted to acknowledge that she was here, and she was very happy of watching Mr. Bridget presentation and also some of the previous presentations. We just came from the field. We are the whole week doing field work in Ibitinga, which is close from here. You have heard about this Pantaninho. There's 2 wetlands nearby Ibitinga. It's 100 kilometers from here. So from here, I'm going back to the field where I have another 3 colleagues, and we are taking samples, doing a drone with thermal sensor, collecting samples for radon. We have a radon lab at the hotel where we take samples in the morning and run the radon in the afternoon. So it's a pretty tough logistic, because we have to jump in a boat, take samples in the wetland, and sometimes also walk in cross sections across this drainage area, which is very tough. We have to go cutting the vegetation and the cipós and espinhos. I don't know how it's espinhos in English. So I'm kind of injured, feet and everything. So it's very interesting. So I just invited Professor Jamil to visit us in one of these days. So who we are from the Geological Survey of Brazil. So I belong to the office in São Paulo. The headquarters in São Paulo City. We are there 200 colleagues, and we are responsible for doing the geological issues in São Paulo State, Paraná State, and also Mato Grosso do Sul. So within the geological survey, almost in every capital of Brazil, there is a headquarter. So in general, in total, we are about 2,300 technicians. Seems to be a lot, but it's nothing. So we are very overwhelmed in terms of activities. We expect a lot, that we have more concourse, to have younger people coming to help us. So this is our desire. So in São Paulo, we have this directory for water resources. So where there are a bunch of technicians, hydrogeologists, and hydrologists. And what we do is we're like similar to the USGS in the States. Those two institutions, they are very similar in terms of their missions. So we do the water water measurements in rivers, groundwater, and also rain. So you have heard about the network, the hydrometeorological network from ANA. So we are the ones that operate. So we get the money from ANA to operate. So we are the ones that go to the field, check the devices, and get the measurements done. So this is very challenging. So this is who we are. So we have different headquarters. I told you already about this. That means also that we have a very strong capillarity across the country. So if we are asked to take samples in the Oiapoque, in the middle of the jungle, in the bioma Amazonas, we can easily go there and take samples. So this is something very nice that puts us in a position to work very closely with research groups, just like your groups, or any group in Brazil, or also with strong partnership with institutions from other countries. So this is something that we seek to work very closely with universities, because we have lots of data and very few people to systematize those data. So I will talk later about this. What else? So yes, in São Paulo we are more or less 40 employees working with water resources, and we are 6 or 7 hydrogeologists. But Andrea, she's a hydrogeologist, but right now she's the boss. So I'm also a hydrogeologist, but 2 years ago, or not so much time ago, I was the responsible for international affairs for the whole country. So we are always split into different activities. So challenges, actual challenges today and for the near future. The first one is to keep the monitoring schemes efficient and assuring reliable data. So Bridget told us in her presentation how important it is to go to the field and take the measurements. So this is our primary mission. We have to find money to go to the field and make people take the measurements in rivers, groundwater, and also the precipitation. Sometimes it's very expensive to do this, and we sometimes we think about, well, how can we do it more efficiently? Working with telemetry or other tools in order to avoid the spending of oil and time visiting all those stations, or even working with remote sensing. I don't know if you have seen the presentation of a colleague of us, Klivik, at the Cabas. He's doing a very nice job working with Grace and benefiting from the levels of our RIMAS network, which is comprised of about 500 something wells, which are equipped, and from there we get like daily level information. So this combination of having this network, which is unique in South America, this is the only governmental network run in South America. So it's very important that we keep doing this, and also perhaps we can start to think about a network like in US they do. They get the USGS in the States. They are the network of the network, so they benefit from river basin networks, and they put the pattern and they make sure that all the levels are getting, the information is standardized. So this is the way that we think we can enlarge our network if we get into agreement with states and river basin committees. So this is a way to move forward. Another challenge is to trying to access and systematize the data and produce useful reports. We are very good in producing data, but we are very not so good in terms of producing reports which are useful for the society. So this is something that we have to look inside, make a reflection, and do better. And not only science reports, but also reports that are good for agriculture, for the industry, for the environmental sector, or whatever. So foster innovation, development, and partnerships with other institutions. This is something that we have to seek. Talking about innovation, right now because we gained the status of being a research institution, so we can run for the calls for FINEP, CNPq, and also raise money with royalties from the oil industry. So this is a big issue. So right now I'm a postdoc working in a Petrobras project with carbon sequestration in the Paraná Basin. So looking for the very saline aquifers, if we find some saline aquifers to do CO2 stocking and storage. So this is a kind of example of how we are trying to do to jump into those innovative schemes and raise money from royalties from the energy and oil companies as well. So hydrogen, the green hydrogen, for example, it's a big challenge also. We can try to find some money to help the country to develop this strategy because of this transition for energy period that we are where we are right now. So examples of relevant studies. There are urban areas and agricultural areas where there are some water issues, areas that are strategic. So we are asked from ANA or from different states in Brazil to do an assessment, groundwater and hydrological assessment. So to raise information and to come up with management framework and management acts. For example, like we are doing in the Verde Grande River Basin in the north of Minas Gerais, for example. It's challenging, it's a karstic framework, and it's not easy to think about integrated models for management in situations like this. In urban areas, we just worked in Manaus, the whole Manaus city, Belém, São Luís, and other places where we do the assessment and we come up with some rules for the management. And this is new for the Geological Survey because we are not used to work with groundwater management. And right now it's like we are trying to do this. And it means also to using any kind of tools like isotopes, radon, drones, and also modeling. So we are trying to catch up with modeling because we don't have still a strong modeling unit inside the Geological Survey. So we are seeking to use innovative tools for assessing water bodies. For example, I told about GRACE, isotopic tools. I'm responsible for a very strong and robust isotope program inside for the whole country. So we are trying to use the same kind of strategies that Didier just showed you with dating and stable isotopes in river, in rain, and groundwater. Yeah, this is more or less what I wanted to tell you. It's a lot of things to do, and we really look forward to have those partnerships with research groups. So we have a very good example on the way we work with the guys from UNESP in many isotopic projects. We can do the same with Edson's group or with any other group. So we are very willing to do this, especially with sharing of information. I think we do we do a nice job in terms of sharing. When we are asked to share information, I mean, it's right away. It's no heavy bureaucracy in terms of sharing information. And also all those tools that we are developing, it's also, we put them available for other research groups. For example, the radon expertise, the noble gas expertise, where I'm an expert in, or any other tool that we have. For example, in the near future, we are going to get a mass spectrometer for noble gases, a portable equipment. So the equipment is going to be there, and feel free to ask us so that we can deliver the equipment and also the expertise to help you in your own project. So this is the idea. Yeah, that's it. Was on time?
Yeah. Well,
good.
Very good, very well on time. I see you still have time for questions.
Yeah, I don't know.
One question.
I also have questions to Mari, to Didier, to everybody.
Yeah, but we will have the Q&A section in the afternoon, so we can start the afternoon with the questions and answers. What do you? Yeah. For sure.
Only because some of us declared old or new waters. So, but it's depending on the usage we use. So, what is for you an old water?
Old water.
Old water. What's a new water? It's depending on the demand we have. I think that's a very short discussion before.
Yeah, there is a formal classification for the age.
Drinking water is old, young water. No treated water is old water.
Because in between there, we have in between 400 to maybe 1,000.
I would take our maximal age for the comparison. So, for example, if a water, it's the same age that I'm supposed to be in this planet, this is a very young water. Any water that's older than my presence in this planet, I would include my son. Okay, it would be an older water, because then if you think about our management schemes, this is the main important issue. So how prepare, how much years further we are doing the planning for today or for the next 10 years. So this is, I think, a reference. Well, at least in my opinion.
Yeah, but it's not opinion for decision makers, because they are using old water. Because you know, they pick the pump water, the treat water, the storage water, and deliver water. But they are losing water maybe in 1 week. They are losing water that's about 400 or more, close to 1,000 years. That is the reality we have there.
Sure. I mean, if you look into the Guarani, you are taking million year water for doing irrigation, for example. Right now in the southeast of Rio Grande do Sul state. So is this fair? Is this clever? This is a question that we have to raise for ourselves.
I don't have anything to add. No. Okay, I have the micro, but I don't have a question actually. I would like to say that something important related to groundwater usage and ages is the plan that the decision makers build. If we think in terms of national decision makers plans, we have 5 years. Only we think on 5 years in terms of water usage. You don't have a renewal of groundwater in 5 years. In other hand, I guess, in my opinion, also it's important to lose water by through pipelines, because this water feeds urban rivers. And if we don't have this leakage of water, probably most of the rivers in the cities will be dry. Or very more polluted than they are.
Abrir a caixinha de Pandora.
Isso rende muito assunto, muita conversa.
Mas eu acho que a gente tem. Sim, entre a gente fala e todo mundo entende. O problema é como você levar essa informação. Quem vai ser? É melhor alguém na frente?
A gente pode, eu não sei, se vocês quiserem indicar, né?